Hello, calculus fans. All right, we're going to try to evaluate double integrals over regions that look like this. The region could be a disk, like what you see on the left side. Or it could be a sector of an annulus. Okay, what's an annulus? An annulus is where you take a disk and then remove from that disk a concentric smaller disk. So then you get like a ring. Then what's a sector of an annulus? Well, a sector of a disk is like a pie slice, like apple pie. Cut up the pie into some slices, that's a sector. So you can do the same thing with an annulus. You can cut it into slices, and that'll give you a sector of an annulus. So we can describe our disk like this. It's the set of all points r theta, where r goes between 0 and 1, and theta goes between 0 and 2 pi. So we're describing the disk using polar coordinates. And then we can describe the sector of the annulus in this way. So it's the set of all points r theta, where r goes between 1 and 2, and theta goes between 0 and 3 pi over 4. These are special cases of a region that's known as a polar rectangle. Let's show what a polar rectangle looks like in general in the next picture. This is a polar rectangle. At first it seems like a very odd name. Why do you call this a rectangle? It's not a rectangle. But it's a rectangle in spirit because the values of r and theta are bounded by constants. Just like a real rectangle, the y values and the x values are bounded by constants. So what we'd like to do is compute this double integral over polar rectangles. The way we'll do this is we'll divide the interval from a to b into m subintervals. They will be of equal width delta r, and we'll divide the interval alpha to beta into n subintervals. Now the circles r equals r sub j and the rays theta equals theta sub k will divide the polar rectangles into small polar rectangles. We can call them polar subrectangles. Here is a division of a polar rectangle into polar subrectangles. You can see I've identified a particular polar subrectangle, r sub jk, and inside that polar subrectangle I've identified a sample point. We'll be talking about that in a moment. Here is one tiny subrectangle. We're going to talk a little bit about how to measure the area of this subrectangle. So the center of the polar rectangle r sub jk has these polar coordinates. R sub j star, we can just average the r coordinates that bound it, and theta sub k star, we can average the theta coordinates. We'll compute the area of this polar subrectangle using the fact that the area of a sector of a circle with radius r and central angle theta is 1/2 r squared theta. Now if we subtract the areas of two such sectors, each of which has central angle delta theta, we'll get the area of r sub jk. Alright, looks like this. So the area of one of these polar subrectangles is delta a sub j, which is 1/2 r sub j squared delta theta minus 1/2 r sub j minus 1 squared delta theta. We simplify, we get something that looks like this. Factor out the r sub j squared minus r sub j minus 1 squared. And if you clean all this up, what you get is r sub j star delta r delta theta. Now we previously defined the double integral in terms of ordinary rectangles. And it's actually possible to show that for continuous functions, we will always get the same result using polar rectangles. Now the rectangular coordinates of the center of our polar subrectangle are r sub j star cosine theta k star r sub j star sine of theta k star. A typical Riemann sum for the integral would look like this. So ultimately we can rewrite delta aj as rj star delta r delta theta. So let's write g of r theta to be equal to r times f of r cosine theta r sine theta. Take care to note that there is an r out in front here. So let's take our Riemann sum and write it like this. So our Riemann sum is the double sum of g of rj star theta k star delta r delta theta. That's a Riemann sum for this double integral. So this is what we get now. So here's how we can evaluate a double integral over a polar rectangle. It's the limit of the Riemann sum that we just talked about, the double Riemann sum. The delta aj turns into r sub j star delta r delta theta. This limit of a Riemann sum turns into a double integral. That's just the definition of a limit of a Riemann sum. But now the important part is that we end up with an expression that looks like this. It's a double integral of f of r cosine theta r sine theta r dr d theta. Notice this r in here. So we can summarize all this with something what we'll describe as a change to polar coordinates in a double integral. So if we have a continuous function on a polar rectangle, and that polar rectangle is given by the values of r go between a and b, and the values of theta go between alpha and beta, and let's suppose that the difference between alpha and beta is smaller than 2 pi. Then, if we evaluate the double integral over r of f of xy dA, we can convert that into a dr d theta integral like this. So we replace x with r cosine theta, we replace y with r sine theta, and then the limits on theta go from alpha to beta, the limit on r go from a to b. So that tells us how to convert a double integral from rectangular to polar coordinates. We have to use x equals r cosine theta, y equals r sine theta. We use the appropriate limits of integration for r and theta. This is, of course, assuming that we're dealing with a polar rectangle. And we'll replace dA by r dr d theta. It's very important to not forget about this r that's in the formula. We'll be talking later on in more generality about where this r comes from. We did talk about it here. It essentially measures the size of the polar subrectangle that we're measuring. Not all of the polar rectangles have the same size. As you get farther away from the origin, those polar rectangles actually get bigger. Okay, that's all for now.